Good afternoon, everyone. Welcome back to Tech Talk Tuesday here at Treadwell. Edward Titley's my name. If you're joining us for the first time, welcome. We run these short 15-minute sessions every second Tuesday where we cover topics related to Australian standards or international standards or applications of FRP or a whole variety of things, really. And if you're joining us again, welcome and thank you. Today we're having a look at FRP versus steel in the wastewater industry. Brief discussion around why FRP might be of value or a benefit in the water and wastewater industry. A couple of cost analysis that are not directly related to the wastewater industry, but nevertheless applicable. And lastly, a couple of photos of completed projects. At the end of all these sessions, we have a live Q&A session. Feel free to put any questions in as we go. I have got the Q&A window open right now, so we can either respond to your question as we go through or address it directly at the end. And lastly, there is a poll that should come up on your screen. If you could please add your comments on future sessions or feedback, that would be greatly appreciated. And any feedback's welcome, good, bad, or ugly. If these sessions are worthwhile, we'd like to know about it. If they're not worthwhile, we'd like to know that too. And as I said, any future content, please always open to suggestions, looking for suggestions on what you would find of value to discuss. So, water and the wastewater industry. So, two aspects to this industry that we would typically work in. One is should we call fresh water or potable water? That might be water treatment from a storage facility, be it a dam or something like that. It might be water treatment from a river or a bore, some other water source to make it safe for use, make it potable water, safe for drinking and other everyday activities. And then obviously wastewater treatment or sewage treatment being treatment of both, so I say domestic or residential, commercial wastewater, but also industrial waste. So I guess really every one of us uses something to do with water or wastewater treatment every day. And as with any industry of that nature, corrosion in the water and wastewater industry, like any processing or process type site, obviously there's chemicals used as part of the treatment process, but then also, especially for wastewater, there's things such as H2S, hydrogen sulfide, that are present, and they will have a corrosive effect on traditional materials such as steel and concrete, and hence FRP becomes a good option for those areas or those environments where corrosion is a challenge. So a few benefits of FRP in the water industry or wastewater industry. Number one is obviously the corrosion resistance aspect. So FRP and typically a V series or vinyl ester resin system with what we use in wastewater. FRP is not subject to attack or breakdown as a result of H2S or hydrogen sulfide exposure. So that solves a lot of issues around coating maintenance, blast and paint regimes, epoxy coatings, or stainless steel. High strength and durability, that kind of ties into the corrosion resistance, which also gives us low maintenance and long-term cost savings. The other thing is FRP is obviously lightweight, which gives us design and install flexibility. The fact that also FRP can be customized or the opportunity to provide bespoke system for your particular project or to use an off-the-shelf or standard product, if you like. And then the visual aspect, FRP being protected against UV attack, giving a good-looking product for a long term or for the future. And lastly, the environmental impact, recognizing that products like FRP require less energy to produce and therefore would contain less embodied carbon than things such as more traditional materials such as steel or concrete. So cost savings, everyone's interested in cost. we'll look at some numbers on the next couple of slides in regards to FRP costing versus traditional materials, because this is a common question, but where you can expect to see cost savings using FRP. Reduced maintenance costs, we've touched on this. FRP's corrosion resistance eliminates the need for protective coatings, coating maintenance, those sort of associated repairs. Lower installation expenses. FRP is significantly lighter than traditional materials such as steel or concrete, which means that either heavy equipment is not required or things like cranes, smaller cranes, would be required, which means that logistic things are a lot easier to install. Also improve safety with reduced weight products. And lastly, extended life cycle. As we mentioned, we have a 55-year case proven design life on our product, and that is case proven by the company who manufactures our resins called Aliaxis, and that application is in a wastewater treatment plant. There's also a variety of accelerated aging tests we can provide, but I think the case proven design life is the most credible or the most valuable. In regards to the question we've got, technical proof of this design life, if you could please drop an email to us. I'll share an email address at the end of this discussion. We'd be happy to send you back that document. Please have a review, and no doubt you may have some further questions, which we'll discuss once you've had a look at that, at the case study around that project. So cost comparisons, these are questions we often get. As I said, these are not directly wastewater related applications, but nonetheless the numbers will still work or still make sense. So first I'll start on the right with the stainless steel solution. So this structure you see here is a full FRP structure. Its predecessor was hot dip Gale with a two-pack epoxy. Its service life was very unsatisfactory, so hence the next options being looked for was either stainless or FRP. So we'll start with the stainless. The cost, excluding the design, engineering, and so on, so the cost of the supply of the structure was $83,000 approximately, divided by 10-year design life expected for a stainless structure in this environment, gives us a cost of $8,300 per year. And that, with stainless in a very saline environment, obviously there's a cleaning and maintenance regime to keep that stainless in good condition and make sure it's durable. Second aspect was that the weight of the structure, be it mild steel or stainless steel, meant that large cranes were required to install. Higher costs, not just with the increased cost of a larger crane, but also, as you can hopefully see from this image, the structure is located in a channel, and to bring the crane close enough to install the steel structure, there would have been some shoring and strengthening works required for that bank, which is also an additional incurred cost. In regards to FRP, so our cost, including design as well, so there was a design cost to go from FRP, from steel to FRP, obviously. So our cost was $91,000 approximately, which divided by 55-year design life is $1,655 approximately per year as for the cost of the structure. That structure is installed with a 55-year design life in that environment. As we mentioned, the significantly reduced weight meant that the structure was able to be installed with just a small mobile crane. None of that bank strengthening work was required. And lastly, the FRP structure was pre-fabricated and also semi-pre-assembled because of the reduced weight, which saved install time and labour on site. And just last thing to think about, no hot work. The modification of FRP doesn't result in any, or doesn't require, I should say, any hot work, which means that no hot works permits are required on site. On this example we're looking at, I believe that the structure being compared to FRP was 316 stainless. The previous structure we mentioned with an unsatisfactory design life was just mild steel. and that was something in the order of 2 to 3 years. I think the lifespan of that structure was, which is obviously not really satisfactory at all. The next option is a cooling tower. Once again, similar idea, perhaps slightly less hostile environment. So, cost of our stainless structure was 25 years in this application. Cost of the structure $380,000 approximately, giving us a cost per year of $15,200. The once again, our associated costs as far as cleaning, maintenance, weight, and just a note here that the previous mild steel structures in cooling tower environments on this site have been noticeably lasting less than 5 years. Now, the FRP solution was approximately $450,000, 55-year design life once again on this site, giving us a cost of about $8,182 per year. That also has a 55-year design life. Couple of things to think about in regards to the weight reduction, a lot lower footing costs. You can see this structure is built somewhat off to the side of a plinth, so a lot lower footing costs and no hot works permit once again required on site. Just in regards to a couple of questions, why the design life of the stainless steel is only 10 years, that's the nature of that site. It's very high humidity, it's very hot. It's in the Pilbara region of Australia, and that was the feedback from the client that their expectation for a design life of a stainless structure was 10 years or less, and that also included a cleaning regime to try and stop the crystallization of salt and so on the surface, which obviously accelerates corrosion. And the person commenting that 316 shouldn't be utilised in a salt environment greater than 1,000 milligrams a litre, agree. But I think the only other option was something like duplex or super duplex, which is, I haven't priced a duplex or a super duplex structure for a while, but I have done it before, and it was something in the order of 5 or 6 times the 316 SS structural cost. So hence we agreed to give a comparison with 316 stainless from a cost perspective being the most widely available option. I'm not sure if that makes sense. Can we show examples of beam to beam and beam to column bracing connections? If we can, I would strongly recommend you have a look at our webinar, the last webinar we did, which was on connections, chapter 8 of the ACMA, the American Composite Manufacturers Association standard, that deals specifically with connections in FRP, and also have a read of the ACMA design guideline. That should answer a lot of your questions around connections. We can provide we have some standard connection examples. However, we would strongly recommend that you look at connections on a project on a case-by-case basis. Feel free to drop us an email on the details we provide at the end, and we'll be happy to send a link to the previous webinar and also a copy of the ACMA manual for you to have a look at. That may also lead to more questions. Happy to discuss those in due course. And I'm aware Olympic Dam's not in the Pilbara. The project we discussed in the Pilbara was at Dampier for Rio Tinto. That was the first example. This example here, I'll just drop back to it. That was for Dampier Salt. And this second project here was Olympic Dam. So at Olympic Dam, they expected the stainless structure would last 25 years. In the Pilbara, their expectation was they'd get 10 years or thereabouts out of it. But absolutely, Olympic Dam's hot and the process water is very saline. In regards to the product coming to the end of its life before a failure occurs, there's various inspections that can be done. Sorry, we're probably getting slightly off track here, but that's fine. There's various inspections that can be done as far as viewing the product. So inspections are purely a visual inspection, and there's various ways to determine visually from looking at the product whether it's reached a point of degradation such that the structural capacity has been affected, as in reduced, or whether it's still serviceable and what you're seeing is normal aging. And then if we determine the structural capacity has been reduced, whether it needs to be replaced or whether there's a repair procedure that can be repair procedure that could be used. If you could drop us an email as well, happy to send back firstly an inspection checklist and also a repair manual to have a look at. As always, this might lead to more questions. Happy to set up a discussion to discuss those further. Another question in regards to environmental impact, end of life. So, good question. When we're looking to issue a white paper on this over the next couple of weeks, but a few things to think about with FRP end of life. Now, there's a very interesting study that's been done by the University of Birmingham. I think it was. There's a link to it on our website under the environmental tab, or feel free to drop us an email again at the end with the email address, and we'll be happy to send it to you to discuss end of life. Now, there's two aspects to that, or there's before I get to that, there's no, shall I say, industry set up in Australia at present to handle the end of life of FRP other than landfill. Now, the reason for that, I would suggest, is because FRP is a relatively new material here. We've seen FRP in Australia a bit over 25 years of life. That's about the oldest FRP around in Australia. So hence there's not the feedstock for an industry to exist to recycle FRP materials. Now, as far as the study the university did, there's two aspects of an FRP product. One aspect is the glass, obviously. Now, glass is glass. The product can be crushed or broken down. Glass can be recovered and used as a drink bottle or a drinking glass or something else in the same way that any other glass product can be recycled. The polymer part, the P part of the FRP is a thermoset polymer, and we need that for heat stability. So it cannot be melted and turned into another plastic item like a milk bottle potentially, or a drink bottle can be melted down and turned into another item of the same. What it can be used for is as a component, as a filler, if you like, for new FRP materials. This is something that's being experimented with at the moment. The most common uses are either as a aggregate for road base or fill, or energy recovery via pyrolysis. Not sure if that answers the question. If you're looking at a particular project here in Australia, happy to workshop around what that end of life would look like based on what's available now here in Australia and what we expect the future to look like. But it's an interesting study, and if you please drop us a line, I would recommend having a read of that, the study done by the University of Birmingham. It's quite a worthwhile read. That's about the end of the session. We've sort of had our impromptu Q&A as we went, just on the way through 3 project photos. This here is our EcoX odor cover system. So you can see this is an interlocking style profile as an odor control cover here, including flashings, various hatches you can see within these handrails, lift out panels for inspections and maintenance and so on of equipment in the tanks. Another odor control cover. You can see some hatches here, various flashings and so on, and also foul air ductwork incorporated, or that connection, that flange incorporated into the cover. And lastly, this is an interesting one here in Wagga in New South Wales. This is the new water treatment plant, been open for a couple of years now, but when it was built, this is the inlet channel from the river water behind this cofferdam or sheet piling. There's gates that are installed in these runners at each end. You can just see them. When the river's low during normal flows, the water just runs in here and gets pumped up to be treated. During a flood event, it would be expected that water would run, it would be a lot higher than the typical inlet level. And so we built this trash screen such that these gates can be put in and water will come in over the top of this channel. These rocks here serve as a start to keep out logs and sticks and so on. And then this trash screen is a full FRP structure with an FRP grating on it here just to facilitate a walkway for safe access down to inspections of these rock installations and so on. It's with the view that these would strain out or keep out any large rocks, sticks, trees, those sort of things from clogging up and damaging the stainless inlet screens you can see down here. And not shown in this photo, however, there is also a handrail along the back end of this, which can be removed as it is in this photo, handrail on the back of here to allow for maintenance access or inspections and so on when that is needing to be done. That's the end of our discussion. Feel free to drop us a line to those, especially I suggest flick us an email. hello@treadwellgroup.com.au is best email address, and we'll get that and send back the relevant information to you. Otherwise, feel free to give us a call, 1-800-246-800 in Australia or 0800-244-600 in New Zealand. The questions have sort of slowed down a bit, so I'm guessing that's about it. Thanks all for your participation and your engagement. Appreciate you coming along. Please, if you could fill out the poll, that'd be good. Any feedback is good feedback. Good, bad, or ugly. Joshua and Martin, you're very welcome. And feel free to drop us a note, and happy to engage in specific project discussions or take you through some design guidelines. Always up for a discussion. You're welcome, Anne. Thanks for joining. Thanks very much, everyone. We'll wrap it up now. Once again, appreciate you joining. Look forward to seeing your suggestions for future webinars, and see you again in a couple of weeks. Cheers.